In the last example, we looked at rearranging the 4-letter words of math. That's a type of combination called a permutation. So what is a permutation? A permutation is an arrangement of n distinct objects in a fixed order in which no object is used more than once. So you can't repeat any object. And the other thing is that the specific order is important. So the order that you're choosing the objects is important, and we can't have any repetition. So for permutation, order matters, and we can have no repeats. So let's look at something. In how many different ways can the members of a family of 4 be seated in a row of 4 chairs? All right, so if I'm thinking about this, this is a permutation because we're looking for a fixed order, and obviously I can't repeat a person, like I can't be sitting in 2 chairs at the same time. So when we go to set this up, let's think about it. So if I had, let's for each chair, 1, 2, 3, 4. So there's 4 chairs. So there's 4 different people for me to choose to plop in that first chair. Now there's only 3 people left for me to choose from to plop in that second chair. Now that 2 people have been sat, there's only 2 left, and then the last person is stuck with that last chair. So when I multiply this all together, I get 24. And notice that this is equivalent to 4 factorial. So formula for permutation. So again, if you're dealing with something where order matters and there's no repetition, which we had here in this example, the number of permutations of n distinct objects is n factorial, and that is n distinct objects can be arranged in n factorial different ways. So I could have just looked at, oh, this is a permutation. I have 4 different people. So the answer is just going to be 4 factorial. So let's do this a little bit more. So in how many different ways can the members of a family of 4 be seated in a row of 2 chairs? So sometimes only some, but not all the objects will be arranged in a specific order without repetition. So if we set up this scenario, we have 4 people to choose from for the first seat and 3 people to choose from the second seat. So we'd have 4 for the first, 3 for the second, which leaves us with 12 options total. And so again, this is still a permutation because the order matters. The order that we're sitting them matters. And we're picking from distinct objects. So there's no repetition. I can't repeat a person. I mean, I wish I could clone myself sometimes, don't get me wrong, but we're assuming that you can't clone someone in this family. So this type, when we have less things to arrange than the number of objects we have, this is called a permutation of n objects taken r at a time. So instead of choosing all 4 of these, we're just choosing 2 of these people out of the 4. So to figure that out, the number of permutations of n distinct objects taken r at a time is denoted by, so you're going to see it denoted in 2 different ways depending on where you're looking at it. Sometimes you'll see it where it's p and then the parentheses n comma r, or other times you're going to see it as subscript n and then a capital P and then a subscript of r. And the formula for that is n factorial over n minus r factorial. So if we go back and we actually use this in this situation, we can figure this out. So in this case, I'm having 4 objects and I'm taking 2 of them at a time. So I'm going to do this in a different color. So my n would be 4 people and I'm choosing 2 of them at a time, and it's a permutation because the order matters and we're not repeating people. So I would write this as P4, 2, or again, you could write it as 4 capital P2. So that formula is going to be 4 factorial over n minus r factorial. So 4 minus 2 factorial. All right, well, 4 factorial is 4 times 3 times 2 times 1. 4 minus 2 factorial is just 2 factorial, which is 2 times 1. Canceling like terms out leaves me with just 4 times 3, which also gives 12. Now, obviously, we didn't need a formula to figure this example out because there weren't a lot of objects we were picking from, but sometimes you're going to get into some larger problems where you'd want to use some type of a formula for it. And I'm going to show you guys how to use technology to do it. So let's look at another example. The Greek alphabet contains 24 letters. How many 3-letter fraternity names can be made with Greek letters if no repetition is allowed? So let's first see if we're dealing with a permutation. So with a permutation, there's distinct objects, which 24 letters, they're all different letters, so we have that. The order matters because obviously if we did like an AKO is very different than AOKI. How many, so the order matters, and we're not allowed to repeat. So order matters and no repeating. So this is a permutation. All right, so in this case, we have our N is 24 because there's 24 options that we're picking from. And our R value, we're choosing 3 out of those 24. So we have a permutation where your N is 24 and your R is 3. So we could kind of do this just by thinking about it. So I want to just show you before I use the formulas how I could do this. So we could use that counting principle. How many different letters are there for me to choose for the first one? 24. How many different letters are there for me to choose for the second one? Well, I've already chosen one, so there's only 23 left. And how many different letters are there for me to choose from for the third one? Well, I've already chosen 2, so that leaves me with 22. Multiplying those all together gives a total possible combination of 12,144. Now, cool, totally can do it in your head. The other thing is you can always use technology as well. So I'm going to show you a picture of me using Desmos on this. So in Desmos, they have this as an actual function, the permutation. So you're going to click when you're in the scientific calculator for Desmos. So that's at desmos.com/scientific. If you choose the function tab, you can find this NPR. That's the permutation formula. That'll come up and you'll put the N value first, followed by the R value, so 24, 3, and you can see we get that same answer of 12,144. All right, let's do another one. How many 5-character passwords can be made using the letters A through Z? First, if no repeats are allowed, and then second, if repeats are allowed. All right, so if no repeats are allowed, this means we have the order matters because it's a password, and there's no repetition. So this means I'm dealing with a permutation for letter A. So this is going to be a permutation where my N value, so how many different letters can I choose from? So A through Z, there's 26 letters in the alphabet, and my R value, so I am choosing 5 of those. So setting this up, I could use Desmos to show that here. So I chose the function. I went down to NPR, which is not showing for some reason in this visual. My N value was 26, my R value was 5, and I got that there were 7,893,600 different passwords. Now, again, I could have done this without using the formula. I could have done it just by thinking. So I'm going to show you that first too. So we'd have 26 options to choose for the first letter, and then we'd be left with 25 for the second letter, 24 for the third letter, 23 for the fourth letter, and then 22 options left for the fifth letter. When you multiply all of those together, you'll also get 7,893,600. Now, if we look at part B, now repetition is allowed. So this is just going to be using that fundamental counting principle. So there's 26 options for the first letter, 26 options for the second letter, 26 options for the third letter, 26 options for the fourth letter, 26 options for the 5th letter. Oh, and that's it. I've done my 5. And you can use Desmos or a calculator to do that as well, and you'll get 11,881,376 different options for a 5-character password.